Hello, hello. I do see a couple of people in online connection. Yeah, thank you. And
Hi, this is Miss.
oh, okay. Hi, Amir. So, do you do you see my screen?
Yes.
Let me check if you see the slides. Do you see the slides right now?
No.
No. Okay.
This is
Then
just the NDSU background, like a
okay.
screen.
Okay. Then let me ask tech support at. Um, is it possible to project video feed from my connection to the major screen?
Yeah. Have you downloaded the? I believe there's an add-on you can get, but you should have the option to share your content.
Okay. Thank you for suggestion.
There you go.
Okay. And let me just check who is. Oh, okay. Rebecca is in the class and everyone else is connecting through online. Hello, Rebecca. Nice to see you. Thank you for investing your time.
Yeah.
Let me, before we start, let me show you the beach and ocean here on the conference.
Oh, where are you, Dr. Clean? Exactly.
It is Georgia. It is a conference in computational chemistry, and I'm just in the hotel room for the lecture.
And the weather looks great for you.
So you still you see my screen, right?
Yes.
Okay, very good. Then if you do not see any the screen, please inform me right away. Stop me, yell at me, because I will be seeing only my slides, and I will not be able to recognize if you do not see something.
Sure.
Thank you.
Yep.
So quality is sufficient?
Yeah, it's okay. For me, it's okay.
Okay. So we are in the course of computational chemistry, and the goal is to predict and describe properties of materials. So we have started with molecular Schrödinger equation for electrons and nuclei, and separated electronic and nuclear degrees of freedom. And now we are going over the Hartree-Fock theory, which is first self-contained logical theory for electronic degrees of freedom only. Before we covered the concept of Slater determinant and spin concept, and today we are slowly starting to pick up the general philosophy of Hartree-Fock theory. You're done with that. This will be the next homework. So this is probably I cannot say what will be the main slide, but the one I'm showing is one of the main. It's maybe summary of the overall Hartree-Fock theory in a very, very simplified way. So I would be happy to redraw this figure, but I think it is not too bad. So let's look on different colors at different instant of time. Suppose that I created it as a movie. So look only on blue colors. So this is blue colors correspond to a molecule which was ionized completely. All electrons were removed. So if it is hydrogen, then it is proton. If it is H2, then it is H2 plus 2 plus. If it is something more complicated, it's just remove all electrons completely. Now, this positively charged nuclei attract electrons. Please have a look on a red schematic curve. Suppose I am throwing one electron to this completely ionized molecule. And if you do not like the idea, please give me some signals. Tell like I am against or something like that. So this single electron will try to localize in spaces around all nuclei, because it will be attracted to all positively charged nuclei, and it will be composed of s orbitals. So s orbitals localized on each nuclei will add together in a superposition and form the lowest molecular orbital. So first electron will distribute near the nucleus. Okay? Good. Now, the molecule in general will still be positively charged. Let's throw the second electron, black color. So since spaces, regions of space near nuclei are already occupied by the first electron, and the first electron screens the Coulomb attraction of the nucleus, it kind of blocks these seeds, these spaces. Second electron will be mandated to occupy a little bit different regions of space. And in this diagram, it is shown that like between atoms, the red line has minimum and black line has maximum. So it's very symbolically represents the idea that electrons interact with each other. There is an electron-electron repulsion there, and it is one of the reasons, in addition to quantization in the field of nucleus, why there are different molecular orbitals. And this is a fact that we need to take into account. So electron-electron repulsion and how it affects shapes of orbitals. Please say if you are okay with this idea. Just okay, good. If someone is not okay, let me know. So this slide is where I would like to arrive by the end of the meeting. So if I will briefly go over it right now, then basically you will get everything we need to cover today. So we will be speaking about pseudo molecule, approximate molecule that has only 2 electrons. Otherwise, it will be 2 nucleus and 2 electrons, like molecular hydrogen. Otherwise, it will be completely impossible to show all details, and we will be wasting time. Full understanding of these 2 equations will become possible at the end of the meeting. But right now, we can just superficially go over it. So the symbols phi1 I am circling my mouse around it. First equation, angular bracket cat phi 1. So first equation is the wave function for the first electron, or first orbital occupied by first electron. Second line, it will be an equation for second orbital occupied by second electron. Our goal that you may remember, or I will reintroduce again, is to chop multi-electron wave function onto some sort of a product of one electron functions, because multi-electron functions are not possible to treat with modern computers. So we need to formulate one electron functions for orbital of electron 1 and electron 2. So although overall state, electronic state of a molecule is contributed by both first and second orbitals, first and second electron, we are trying to chop our electronic Schrödinger equation onto two equations. One which will be for electron 1, second will be for electron 2. And main feature of this equation correlates with the previous slide. So if we formulate, I'm going to lower lines, if we formulate equation for electron 1, it will include Coulomb repulsion from the field, from the density, from the electrostatic repulsion created by electron 1, which is in orbital 1. If we are looking for state for orbital for electron 1, it will include influence Coulomb repulsion from electron 2, which is in this rectangular brackets. So since I do not see your faces, please confirm if this idea is okay and if it sounds reasonable. Okay. And if someone is not okay, please let me know so that we do not waste any of the attendees. Okay.
Yes. Dr. Kevin, I have a question.
Please.
So one specific orbital can hold 2 electrons, but for this equation, we just assume the 2 electrons in different orbitals, right?
Right now, we temporarily neglect spin properties.
Okay.
If we, there is a way to include spin, but for simplicity, we assume that we just do not know. There is no spin, or at each orbital there are two. Well, we are doing abstract mathematical concept, because if you have 2 orbitals and spin is allowed, then we need like 4 states. Will be too many slides to show.
Okay.
Okay. Going back to slides. So I have slides to review what we did. So Slater determinant, justification through the spin, and Slater determinant we have in the rows we have orbitals 1, 2, and so forth in the columns, and in the rows we have numbers of electrons, first, second, third, and this is spin properties that you have successfully completed and sent homework. This image, it is what likely Dr. Han will offer you to do on Wednesday night. And now we are continuing to describe the potential created by already deposited electron on new electrons that will be deposited later. So there is an idea that orbitals that are already occupied create additional field. And if we fabricate a procedure that will include influence of other orbitals on our primary orbital of focus, then it will be a good basis, good building blocks for subsequent formulation of multi-electron wave function. So the most complicated thing in this construction is electron-electron interaction, Coulomb interaction. When we were writing down the Hamiltonian, we were putting like 1 divided by absolute value of difference between position of one electron and second electron, or first and third, or if you have multiple like I and J. So this is, and we do not write any factors in front because we are in the atomic system of units. The sign is plus because electrons repel each other. In the intuitive common sense, Coulomb law should have charge 1 localized at position 1 and charge 2 localized at position 2. I'm going to look if everyone agrees with this. Right? So Coulomb law is Q1, Q2 divided by distance between them, right? So if we are going to quantum case, then instead of point charge, it will be probability distribution, which is wave function squared. So we will have wave function for the first electron, absolute value square, which will be density, like charge. And here there will be wave function of second electron, absolute value squared. And then if we want to find the value of Coulomb interaction energy, we need to integrate over the position of R1, dR1, and over position of dR2, so two-dimensional integral. I'm going to make face-to-face screen once again. So, what you may again think that your instructor is silly or disfocused. So, what will be the sign of total Coulomb energy for interaction of two electrons in orbital 1 and orbital 2? Sign.
Negative.
Two electrons are repelling. The term in the Hamiltonian is positive. 1 divided by absolute value of R1 minus R2. So even if in the denominator is negative value, absolute value is always positive.
Okay.
Amir?
Yeah.
Plus or minus?
2 electrons, so they have negative charge. Why?
But they are repelling, right? They both have negative charge.
Right.
So if energy is negative, it means they will attract. If energy is positive, they repel.
Negative, totally the energy should be positive, right?
Yes, yes. So the intuitive analysis tells us that it should be positive energy.
Right.
Right. So I agree with you. But we will go over a concept, how the Coulomb interaction of two charges of the same sign can be negative. So the suggestion to have it negative was not wrong. I was just checking that it was right for right reason. So I'm just I want to focus your attention on the sign of the Coulomb interaction energy between two electrons.
Okay.
Okay. Going back to slides. So the plan is to represent multi-electron wave function, which is too complicated, as a product of one electron wave functions. Orbital electron 1 in orbital 1, orbital 2 in electron 2. And we could take more, but for today's example, we will limit ourselves to this product. And we already, later on, we will remember our knowledge about antisymmetry. Without antisymmetry, one cannot survive. But right now, I'm trying to simplify the narration as much as possible. So here is electronic part of the molecular Schrödinger equation. Kinetic energy of electrons, T sub E, in attraction of electrons to nuclei, and repulsion between electrons. So this Hamiltonian acts on a product of wave function of the first electron and wave function of the second electron equals energy times product of wave function of first electron, wave function of second electron. Make sense?
Yeah.
Okay, at least it is what we were doing before. But our goal is to escape to electronic wave function. And if one needs to get rid of a wave function, at least one of them, there is a procedure how to convert wave functions into numbers. And this procedure is used in Ehrenfest theorem and in the Heisenberg equation of motion. So let's play the Wheel of Fortune and guess what is under the yellow boxes.
It's a lottery.
Yes, yes. So there are two words. First word is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 words, and the second is 5 words. So suggest a letter, or give the complete word. So how to get rid of wave functions? How to find observables in quantum theory? This right after this yellow boxes, there is an equation that implements it. So one just needs to name this procedure. Since it is a long word, you can try guessing any letter.
If you show the first letter, then it would help maybe for the rest of this.
Okay. First letter E.
Eigenvalues or eigenvectors?
No. Raju, Rebecca? No. It is more general procedure for any observable, not only energy. It will work for position, for momentum, for angular momentum. Do not. No. Try a letter by letter.
Experiment.
Word X was correct. P was also correct.
Yeah, experiment.
Let's continue. Fourth letter is E. But I just assure you that the next letter is not R.
Exponential. No.
Just tell a letter. It is something that one is waiting to obtain if the experiment is being performed. Like average, long waited. Just a second. Please call in 1 hour. In 1 hour. Okay? Thank you. So, any suggestions? Try to randomly use letters. Maybe it will help.
O.
O? No, there is no letter O. I?
Yes.
Yes.
Mm-hmm. R.
No.
A.
Yes.
It's not the value. The last one is value. The last
Correct.
Value.
Oh, I was wrong. There is one more letter.
Exponential values?
No.
What is the fourth letter after P?
E.
E. Expectation, yes.
value.
Yes, expectation value. So expectation value, it is a procedure that helps to convert wave function into observable. And now, please, typically, this expectation value procedure is designed for one variable. So wave function of one variable is converted into a number. But now we do have operators that depend on two independent variables. And we are going to make a very cheesy trick that will help a lot. So we will do an operation halfway. We will partially convert operator into a number and partially keep it as wave function. So we will perform this expectation value procedure over variable R2 by multiplying by bra and cat, but we will touch the variable R1 unchanged. So in respect to variable R2, it will become expectation value. In respect to variable R1, it will be still an operator. So it is like a monster, half number, half operator. Okay. So so it will be a monster science.
It's a very long time it will take me.
What?
Thank you for all the help. Otherwise, it's not going to work. The motivation really helps.
Is it one of participants of the lecture or someone else?
No, I think it's another student in the open office.
Oh, okay.
Yeah.
Okay, so continuing. A monster, half operator, half number. So let's look on the top line. Let's look on the top line and only on red writings. So if we take only red, if you take only black writings, it will be operator which is Hamiltonian for 2 electrons acting on the 2 electron wave function, giving eigenvalue and 2 electron wave function. Now we are going to apply our trick. We multiplied by bra for the second electron. This bra phi 2 from the left, and here bra of phi 2 from the left. There are no rules that prevent me from doing it. It's just we can do this little mathematical experiment. Now let's keep doing this operation separately for each term in the Hamiltonian. So for kinetic energy of electrons, for attraction between electrons and nucleus, and for electron-electron repulsion on the right side. In the left side, the convolution of orbital 2 bra and orbital 2 ket will give 1. So it will be just removed. And this monster, which is partly operator, partly number, we can call it reduced operator. So let's focus on each term separately. Kinetic energy. So 2 electron kinetic energy is summation of this differential operator derivative over position of electron 1, differential operator position of electron 2. If we are performing this monster operation, if we make this reduced operator in reducing over coordinate of second electron, the part T sub E1 will remain the operator, and the convolution of wave function of 1 electron wave function for orbital for electron 2 will convolute into 1. So after this operation, kinetic term for first electron will not change. But if you will apply this procedure to the second term with derivative over x2, second derivative over x2, then this operation, which includes second electron, will give a number, will give the expectation value of kinetic energy of the second electron. And we will symbolize it with the angular brackets. So if we have hat on the top, it will be operator. If it is enclosed into brackets, it will be a number. I'm going to look on your cameras to see if no one is protesting. Okay? Operator and number. It's just the same thing. Now, if sorry, there is no nice type writing, but the content is correct. So if we consider attraction between nucleus and electrons, V sub Ne, there will be 4 terms. Attraction between first electron and first nuclei, first electron and second nuclei, second electron first nuclei, second electron second nuclei. We can call them this way, V sub N1 E1 and so forth. Now let's apply this monster operation, finding expectation value in respect to second electron to each of these terms. So I'm looking on the second line and I'm rotating my marker, my cursor around it. So if we perform an expectation over coordinate of second electron for the attraction between first electron and first nuclei, the operator does not depend on second electron. Therefore, we put operator out of brackets and bra and ket convolute, and we are obtaining operator that acts only on electron number 1. if we do the same operation for attraction between first electron and second nuclei, it is the same convolution happens, and it remains an operator, attraction between first electron and second nuclei. But if we apply it to the last and second last lines, attraction between second electron and first nuclei, and then we cannot put the operator out of brackets. It will be integration. So this bra and cat notations means integration over variable R2 lowercase. Therefore, after this integration, it will be a number, expectation value, this angular brackets of V sub N1 E2. And the same for the attraction of the second electron to the second nuclei. We cannot put the operator out of brackets, so we will obtain a number, angular brackets of V sub N2 E2. I'm going to look at cameras that no one is protesting. Make sense? More or less? Okay. And the last term, interaction between electron 1 and electron 2, lowercase. So if we apply this monster procedure of partial expectation value, partial convolution over position of second electron, this is equivalent to integrating over R2. This will be a true monster. It will be integration over variable R1, but 1 over R integration over R2, but 1 over integral R1 will still be in the denominator. So this will be this half number, half operator. So I'm going to bring cameras once again, and I hope you didn't get discouraged yet. So why this operation is needed? If we do pure Coulomb operator, in order to find expectation value, to find energy, one needs to multiply this 1 over delta R by how many wave functions? 4. So 2 wave functions in state 1 for electron 1 and 2 wave functions of electron 1 state 2. Totally wave function in the 4th power. And if you want to deal with only one electron wave function, all operators are typically referred to two indices, two indices and one independent variable. So 4 indices and 2 independent variables is just too hard for us. We need to simplify Coulomb interaction. And this mathematical trick just represents the first figure that we discussed. First electron is already sitting on the nucleus and creates an average field that repels the second electron. So it is an operator that acts only on the second electron. Okay? Good. So we are not very far from what we are doing. Now I'm going to subtract. I'm going to reformulate Schrödinger equation for electronic part for Schrödinger equation by subtracting, bless you, by subtracting all expectation values from Hamiltonian and from total energy. It is if you were practicing some classical mechanics in high school or in college, like physics, basic classical mechanics, you know, and even without any background, for Newton equation of motion, force is equal to gradient of the potential energy, right? Correct?
Yes.
With minus sign. So if we add a constant to your potential energy, the gradient will not change, because derivative of a constant is 0. So if you change energy by a constant, all equations will stay correct. So I do have this freedom, and I want to practice it. I will subtract expectation values from the energy. So I will take the eigenvalue of energy and subtract kinetic energy of second electron, and attraction between first nuclei and second electron, and attraction between second electron and second nuclei. Wait, just a second. And the same thing, I can do the same trick by subtracting everything relating to the first electron, just for symmetry. So I can subtract either all expectation values related to the second electron or expectation values related to the first electron. It's there is no physical meaning. It's just my freedom to subtract constant from the energy. Then, if I have subtracted the constants from both operator part, from left part of the Schrödinger equation, and from the right part, which is expectation value, then we are obtaining a magnificent equation that is literally originates from many electron Schrödinger equation, but now it acts only on electron number 1. All constants related to the second electron are hidden into this eigenenergy. All operators related to the second electron have been subtracted from the operator part. So look here. In operator part, there are things that relate only to the first electron. Kinetic energy of the first electron, attraction between all nucleus and first electron, and repulsion between second electron and first electron, which is included explicitly. So this is Schrödinger equation, which is in mathematical sense a one electron equation. It has one independent variable. And this is a big achievement. We do not have the procedure to solve it, but if we continue in this way, we will be able to be champions. Because one electron Schrödinger equations can be solved. Analytically or numerically, we have enough computer power to solve one electron Schrödinger equation at any time. The only trick that we implemented here is that all other electrons except our favorite electron do create an average repulsive field. This is an approximation. This is not like absolutely perfect, but this is a very good approximation. We pave a way to find electronic states of any molecule and material. If you want to object or ask questions, you may do it right now. No, okay, I'm going further then. So if you look on the second line, it is very symmetric. I just replaced index 1 with index 2 everywhere, swapped indices 1 and 2. So now we have explicit equation for electron number 2, and we removed everything which relates to electron 1 except the average field. So here we integrate over position of electron 1 and it creates an average field. But if we replace this R1 and R2 by different variables, x and y, in mathematical sense, these two equations are equivalent. So we do not need, in fact, we do not need to solve one electron equation for as many electrons as we have. We need to just solve one electron equation, and since it is a Schrödinger eigenstate equation, it will have many solutions. And if you carefully formulate this equation, these many solutions will be orbitals, building blocks. By setting up products of these orbitals, we will get many electron wave function. And it will include interaction of electrons to each other. Make sense? If it doesn't make sense, if you feel negative emotions about this idea, it is very normal. I first heard this idea on like third year of undergraduates, but I was resisting and feeling negative about it for next 10 years. It's very unnatural. So the concept is we are using it for Hartree-Fock theory, but in general this concept is referred to as mean field. Mean, not like mean to us, bad to us. Mean like average. So average field created by electrons that are already occupying spaces near nucleus create an average mean field that repel the last electron. Okay, let's see if I have more slides. It is not yet end. I have a couple of illustrations that you may enjoy. Remember, we were illustrating antisymmetry by product of sine 2x and sine x. You remember this? Okay, I'm going to give a little heads up and illustrate the energy of electron interaction in this simple example of two electrons in one box in a particle. This is the last equation was the main take-home message for today's meeting. Whatever I'm going to show will be more like entertainment and heads up for the next meeting. So if you are tired or busy, you can lean back and relax. You will not lose much. Okay, so those are just products of wave function sine and double sine with swapped order, but they are not symmetrized. If we subtract this sine times double sine and then double sine times sine into antisymmetric wave function, look, it will have 0 along main diagonal, while before symmetrization it was both positive and negative along main diagonal. And this is an important feature. So if we formulate a Coulomb operator in this system of coordinates, x1 minus x2, it will have discontinuity at the point where x1 equals x2. And if you take absolute value, 1 over absolute value x1 minus x2, it will be also discontinuity, but it will be positive along main diagonal, and then it will decrease, getting smaller and smaller. Now, let's find total energy of electron interaction for so this is just normalization. If you take absolute value squared of this multi-electron wave function, then it will be everywhere positive. But if there is no antisymmetrization along main diagonal, it will have non-zero values. Now, if we will find expectation value of the Coulomb repulsion of two electrons, in the denominator we will have this x1 minus x2 absolute value. In the numerator we will have this two electron function absolute value squared, and then we integrate over x1, x2. So if it is, there should be just a second. I need to correct myself really quick. Sine x and sine 2x. So if we perform this integration, we have the function that is non-zero on the main diagonal multiplied by Coulomb function, which is infinitely high at the main diagonal. So we make two-dimensional integral over function that takes the infinite values. And if we perform this operation according to this black MATLAB code, the answer gets not a number, it will be infinity. If we do it for molecules rather than this particle in the box, it will be not infinity, but it will be unphysically big number. Now, if we take antisymmetric wave function, the main feature that along main diagonal it is zero. And if we multiply it with Coulomb operator, which has infinity along along the main diagonal, we multiply this infinity by zero, and we get still zero along main diagonal. And if you carefully perform this integration, it will get some small number. It is positive, but it is not infinite. This will be a subject of our next lectures. So if we want to build Hartree-Fock theory, we have two major components. One is chopping wave function on the multi-electron wave function on products of one electron wave functions. And second one, use antisymmetry principle. So all equations that we considered today did not use antisymmetry. And there is a last illustration that I did show you demonstrate that if one gives up antisymmetry principle, then energies will be too high. It will be unphysically high, and it will give qualitatively wrong results. So it is important to integrate the antisymmetry principle into this mean field concept. And basically, Hartree contributed mean field idea, and Fock contributed antisymmetry. Therefore, it is Hartree-Fock. Okay, I'm done. Everyone is free to leave. I will stay here to answer any questions, and after answering the questions, I will try to save recordings and share with you. Questions?
So today, tomorrow also we will have a online lab session, or
no? What? It will be a regular lab session. So a postdoc from my group will come and show you how to launch Hartree-Fock calculations. It is not too hard. Some of you may already did it. I am confident that Rebecca did it many times. So she will be probably helping others. Any other questions? Okay, if no, then or if you generate more questions, you can send me by emails. I love emails. And so tomorrow evening, please come as usual to the lab. There will be Dr. Han is very quick. He typically does things quicker than I do. And on Thursday, we will have the lecture number 12 in the same format.
Okay, so enjoy your conference and also your trip.
Oh, thank you. Thank you. Yeah. Have a nice day.
You too. Bye.
Bye. Last chance for questions. Raju, no questions? Rebecca, no questions? Mahek, I will share the recording, or if you want, I can briefly go over slides, but if you saw, let me show you the main slide and ask if you have seen it. If you did, please let me know if you have seen this slide. Last three slides. Okay, then I will quickly repeat the meaning of this slide, and the rest was just motivation where it comes from. So we do have two equations, top and lower. Originally, we are building multi-electron wave functions for the first electron and second electron. But we want to represent, for simplicity, to make it doable by computation, we want to represent, to separate variables, to represent multi-electron wave function as product of one electron orbitals. And here we are formulating such equation that will allow us to find only orbital for the first electron in the first line, and only orbital for the second electron, second line. So if we look here, there it looks like a regular Schrödinger equation. So there is an operator, unknown wave function, eigenvalue, unknown wave function. So everything that is enclosed into a box acts only on the first electron. So it is kinetic energy of the first electron. Here is attraction between all nuclei and first electron. And here this symbol phi2 means that we have integrated this Coulomb repulsion over position of second electron. So this term, corresponds to the second electron creating a repulsive field that drives first electron a little bit away. That's it. And the second equation looks very much similar. So it has, this is an equation for second electron, unknown wave function. Everything inside the box acts only on second electron. Kinetic energy of second electron, attraction between nucleus and second electron, and repulsion of the second electron from the first electron. So there is an average field created by repulsive field created by first electron and acting on the second electron. So if you solve this top and lower equations, we will find this phi1 and phi2 and plug them into this product. And this product will serve as the approximate two-electron wave function. So this is this is called mean field idea that was contributed by Hartree, and one needs to combine this idea with antisymmetry principle, with later determinant. And this was done by Fock. And if you merge these ideas together, it will be Hartree-Fock theory that allows to find wave functions and energies of electronic states. Okay? Any questions? Okay, very good. So tomorrow there will be lab by Dr. Han, and I think he typically does everything much quicker than I do. On Thursday it will be the same online format, and the next week I will be back and we will continue as usual. Okay. Yeah, thank you very much. If there are no more questions, then I'm disconnecting. Okay, thank you. And thank you to tech support for the help. Have a nice day.